Hey guys, I'm going to cover the acids and bases PowerPoint presentation. So let's get started. What are some major characteristics of acids? Well, let's think about lemons. Lemons have citric acid. And what happens when lemon sometimes gets in your fingernails, or let's say you have a cut of some sort and some lemon juice gets in there, it tends to burn. Okay, so they have a burning feeling. And what about taste-wise? Well, they taste sour. Okay. Now, when any acid reacts with a metal, right here we're looking at this tab right here, when any acid reacts with a metal, it produces hydrogen gas. Any metal, no matter what, if you react an acid with a metal, hydrogen gas will be produced. Now, what happens when you react? Let's go to this one. An acid with any sort of carbonate, like baking soda, that's sodium bicarbonate, right? What happens there? Well, any carbonate that reacts with an acid produces CO2. Metal produces H2 gas, carbonate produces CO2 gas. All right. Okay, major characteristics of bases. They taste bitter. They feel slippery. Think about soap. These are all your cleaning supplies. Okay, those are your bases. Okay, taste bitter, feel slippery. All right, now, here it says, can acid or bases have electrical properties? And yes, they do. Okay, acids and bases are electrolytes. Okay, why are they electrolytes? Well, they have those free-moving ions. Okay, if they have those free-moving ions, they're able to conduct electricity. So that must mean that acids or bases dissociate or ionize in solution. They separate into ions in a solution. Okay. So let's say we were dealing with HCl. And I'm just going to do a little beaker of HCl right here. Okay. If we have some HCl, let's say in water, in H2O. Okay. Well, the H and the Cl, they're going to separate into ions. And you're going to have ions in solution. And if you have ions in solution, they're able to conduct electricity. These are electrolytes. Okay. All right, now, the next tab. It says acidic, basic, and neutral solutions are based on the concentration or amount of H plus and OH minus in an aqueous solution. So we talk about acids and bases with the concentration of hydrogen ions or the concentration of hydroxide ions. So what does that mean? Well, an acidic solution is going to have a higher concentration of H plus ions. A neutral solution, they're going to be the same amount. A basic solution is going to have more OH minus in solution. So your hydrogen, your H plus ions, those are your acidic ions. And then OH minus, those are your basic ions. So if you have more OH minus, you're basic, more H plus, acidic. If you have the same amount, neutral. It's always based off the concentration of those ions, and that's one way to detect if something is an acid, if something is a base, or if something is neutral. Okay? All right. Moving on. Okay. Here we have kind of a simple example. Okay. Any sort of acid goes into water, we're gonna have a surplus of H plus ions in solution. We're gonna have a high concentration of H plus ions in solution. On the contrary, if you look over here, if we put a base in water, we're gonna have a higher concentration of OH minus in solution. And like I said, this is just one way chemists identify acids and bases. This is one way, through the concentration of H plus and OH minus ions. Okay, moving on. Some more properties of acids and bases. You may have heard of litmus paper before, or some sort of test that tests for if something is acidic or basic. A lot of you have pools. The old school way was litmus paper. Okay, litmus paper, it comes in blue and red. So blue litmus paper, it will turn red in the presence of an acid. Red litmus paper will turn blue in the presence of a base. So there's different types of litmus paper in order to determine if something is an acid or if something is a base. And you may be familiar with this. You may or you should have worked with litmus paper in your biology classes. Okay, now, cabbage juice actually has indicator properties. Well, what's an indicator? These are all different types of indicators because they change colors in the presence of an acid or a base. It indicates the pH of a specific solution. Okay? It can test for a wide range of acids and bases. Okay, so what you do if you want to obtain that indicator from cabbage juice, all you got to do is get some boiling water, break up some red cabbage, put it in your boiling water, let it sit for a while, let it cool, and then go ahead, pour it into your beaker, and that juice will have indicator properties. So if you were to use that indicator juice or that red cabbage juice in the presence, let's say, if you put some lemon juice in there, it's going to turn colors. Okay, well, what color is it going to turn? Well, here we have a scale we can look at. If it's turning more green or yellow, it's going to be more basic. If it's turning more reddish or pink, it's going to be more acidic. So you can actually determine the pH based off of its color. Okay? All right, those are indicators. And remember, this cabbage juice it's a universal indicator. It's a universal indicator. We can use it for a wide range of acids and bases. Okay, now, this one gets pretty tricky, but you've seen these before. Okay, these are neutralization reactions. Okay, neutralization reactions happen when an acid reacts with a base. Okay, anytime an acid reacts with a base, a salt will be produced and water will be produced every single time. An acid and a base react to form a salt and water every single time. These reactions are just double replacement or double displacement. That's all they are. That's all they are. Taking this example right here. Okay. If we react hydrochloric acid, that's HCl, with sodium hydroxide, that's NaOH, the result will be a salt and water. So what you can do right off the bat, every single time in these neutralization reactions, because you're going to have to predict the products, is just write down water every single time. Because water is going to be produced every single time. Every single time. That's going to be one of the products. Okay, now you just have to figure out the salt. Well, if I told you it's a double displacement reaction, we know, and this is kind of, let me clean this up a little bit so you can see what I'm talking about. And I'm going to use a different color. Let's use purple. Okay. Remember, H will replace here, boom, and then the Na will go with the Cl. So that's why HOH, that's water, got that. Remember I told you to write that down first. And then what's salt? Well, we got Na and Cl reacting. It's not going to be ClNa. We know that cation goes before the anion, so it's going to be NaCl. That's a type of salt. Specifically, we know that's sodium chloride, that's table salt. But remember, a salt is any ionic compound, any cation and anion, any metal and non-metal, right? So our final chemical reaction is going to be NaCl plus H2O. Now, remember when we do double displacement reactions, things we need to make sure of. Okay, we need to make sure this is balanced, or this is a neutral compound. Okay, well, we know the charge of Na is plus, the charge of Cl is minus. Are we good? Yeah, we are good. Next thing we have to kind of make sure Is this balanced? Well, we got one H over here. We have one H over here. We have two H's over here. We got two H's over here. We got one Cl over here. We got one Cl over here. We got one Na over here. We got one Na over here. We have one O over here. We have one O over here. Okay, so we know it's finely balanced. So these take a few steps. It's your normal predicting the products, making sure what you've made is a neutral compound, and then finally balancing it at the end. Okay, make sure you have the same amount on the products and the reactant side. Okay? All right, let's move on to the checking for understanding. Okay, so neutralization reactions, I'm just going to do a few of these. And then you have the answers to these on your PDF that I posted. Okay, so let's go over the first one. It says, I'm going to do this product in green. Okay, so it says HCl reacts with KOH. That's hydrochloric acid and potassium hydroxide. So before we go about this, you may ask, Mr. Mitchell, how do we know things are an acid or things are a base? Well, number one, you'll get familiar with me going over certain ones, so you'll recognize them, but you can also recognize the way they're written, right? Remember, acids have that H plus ion, so you see that H is in front. Most of the time when that H is in front, you're dealing with an acid, so HCl is an acid. You see this OH, we know that OH minus is that ion for bases. So KOH, it's a base. So those are ways you can detect acids and bases, just the way they look. Okay? All right, moving on. So remember, every single time I told you just write down water because it's produced every single time. Okay? Now, what's it going to react with? Well, it's going to be some sort of salt. What salt? Well, we know H went with OH. That means K goes with Cl. So we're producing KCl. All right. Well, it's KCl a neutral compound, but the charge of potassium is +1. The charge of Cl is -1. Guess what? Yep. That's neutral. Let's make sure everything's balanced. I've got 2 H's on the left, 2 H's on the right. 1 O on the right, 1 O on the left, 1 Cl on the left, 1 Cl on the right, 1 K on the right, 1 K on the left. We are good to go. Okay, moving on. H2S reacts with LiOH to produce, and I made a mistake here. I wanted to do this for you, so just ignore that for now. I forgot to erase that off the answer key. So it's H2S reacting with LiOH. Okay. All right. Now, which one's the acid? Which one's the base? Well, you see that H is in front. That's going to be our acid. This is going to be our base because we see that OH. Okay. Remember, every single time water is produced, write it down. You may say, oh, Mr. Mitchell, well, this is H2 reacting with OH. That's 3 H's. And no. Okay, we're going to make up for that last H when we balance it. Okay? Water is produced every single time. Every single time. Okay. So, H2O is going to react with, or get, the byproduct is going to be H2O and some sort of salt, right? Well, what salt? We know that H's go with the OH. That means the Li goes with the S. So it's going to be LiS. Now, let's make sure that LiS is an actual neutral compound. We know the charge of Li is +1, but the charge of S is 2-. So that means there's going to be double the amount of Li. We got to put Li2S. All right, now we're good there. Now we're going to make sure this thing's balanced. So we have 2 Li's over here. That's why we put a 2 here. Now, that makes 2 O's, 2 H's, and 4 H's. So we need a 2 here. Now we got 1 S, we got 1 S. The rest is good. This is how you do it. okay? All right, let's do one more. HBr reacts with MgOH2, and what does it produce? Remember, every single time, write down your water, because a salt in the water is produced every single time. Oh, whoops. All right, and then what kind of salt? Well, we know the H goes with the OH, the Mg goes with the Br. So MgBr. Just write it down right off the bat. Don't worry about your subscripts yet. We'll worry about that when we're trying to neutralize this specific salt. So the charge of Mg is 2 plus, and the charge of Br is 1 minus. So what do we got to do? We got to put a 2 here. Got to put a 2 there. And we're good to go. Now we got to balance it. All right, we got 2 Brs on the right. We need 2 Brs on the left. Boom. Now we have 2 H's and another 2 H's. So that's 4 H's. So let's put a 2 here. Boom. Okay. Now over there we have 4 H's. 4 H's, we're good. Okay. Now we have 2 O's. We have 2 O's, we're good. We have 2 Brs. 2 Brs, we're good. 1 Mg, 1 Mg, we are good. Okay, this is how it is. All right. So if you have any other questions on that, let me know. I'm going to move on. Oh, that should be bell work. Okay, so the bell work. If there is a higher concentration of H plus ions than OH minus ions, the solution is considered acidic. If there's more H plus or a higher concentration of H plus ions, it is considered acidic. Okay, number 2, acids and bases are said to have electrical properties. Why is this? They have those free-moving ions. Free-moving ions. So they dissociate or ionize. They have these free-moving ions. Those free-moving ions are able to conduct electricity. Okay, number 3, what is always produced during a neutralization reaction? We just went over this. Salt, any sort of salt, and H2O, and water. Salt and water. All right, moving on. Now, I'm going to break up the video. I'm going to go ahead and pause it here, and then we'll go ahead and start the next video so I can break these up so they're not as long. All right, so Bronsted-Lowry model of acids and bases. How do acids and bases behave? Okay, now, this Bronsted-Lowry, this is just one of the models, okay? These chemists decided, okay, we've been studying acids and bases. We want to give our own definition of what it means to be an acid or a base. So this is just one of the models. There are multiple models. Remember when you read that superacids reading, it was all about Lewis and how he thought acids behave or how bases behave. So a lot of different chemists have these different theories about and models of how acids and bases behave based off their experiments. And we're going to study a few of those. Okay, so the first one is that I want to study with you guys is the Bronsted-Lowry model. The Bronsted-Lowry model of acids and bases. So Bronsted and Lowry decided that acids act as hydrogen ion donors. Hydrogen ion donors. They're going to donate that H plus. They're going to donate that H plus. Okay. And when they donate that H plus, okay, this water turns into H3O plus because it gained not only an H, okay, but it gained a positive charge. So, showing this again, an H plus, this HCl is the acid, we're saying that it donates an H plus, so this HCl loses not only the H, but that positive charge. And it gives it to the water. So the water is now H3O plus, okay? And what's left of that HCl, well, it lost the H plus, so it's now Cl minus. Okay? And these are known as the conjugates. Whatever's produced, those are the conjugates. Okay? What an acid or base turns into are the conjugates. Okay? All right, now, this H3O plus is known as hydronium. Okay, hydronium and hydrogen, they're the same thing, okay? They're the same thing. It's just hydronium, it shows that the H plus is attached to the water. Okay, it's actually attached to the water. When we say there's just actual H plus in solution, we're basically saying the same thing. It's an aqueous solution. So H3O plus and H plus, they're the same thing. Okay, we're just saying that H3O plus is when water is actually gained the H plus, but they're the same exact thing. So if you see H3O plus in solution, or if you see H plus in solution, you see a high concentration of H plus in solution, or you see a high concentration of H3O plus in solution, that means it's acidic. Okay, we're just showing that in this chemical reaction, the H plus, okay, is being donated to that water, so we're showing that. Because this is Bronsted-Lowry's model. And what I'm saying is don't get confused though. The H3O plus represents the H plus. Okay, it's the same exact thing. Okay? All right, hopefully that made sense. Moving on to bases. Bases are hydrogen ion acceptors. So find your base. NH3 is our base. Okay, it's going to accept NH plus. It's not going to donate, it's going to accept. What's it going to accept it from? Well, it's reacting with the water, so it's going to take one from the water. So if an H plus has been given to the NH3, it now becomes NH4 plus, because it didn't only gain an H, it gained a positive charge. Now, this water over here, it lost an H plus. So it's no longer H2O, it's now OH, and it lost a positive charge. Whoops. So it's OH minus, and this is our hydroxide ion. So if we see hydroxide ions in our products, okay, we've done it correctly. We're dealing with the base. If we see H3O plus in the products, okay, we've done it correctly. We're dealing with an acid. Because we know if those are in solution, based off this Bronsted-Lowry model, that we're dealing with an acid or a base. Okay, and here's your key terms for this section. Dissociate, to separate into ions. The hydroxide ion we've talked about is OH minus. The hydronium ion is basically the same as the hydrogen ion. It's that H plus is attaching to the water, and then your conjugates are what they turn into. So your products, those are your conjugates, what the acid or basis turns into. So how do you write? These are dissociation equations. How acids or bases should dissociate. How do you write these, and how do you label these? Let's take a look right here. Okay. HF, what does it look like? Well, the H is in front. It must be an acid. So we know that acids are hydrogen ion donors. They're hydrogen ion donors. So it's going to donate that H to the H2O. Remember, H plus, H plus. So if it donates that H plus to the H2O, it becomes H3O plus. Well, that's not the only product we have. We also have whatever's left. And if it donated the H plus, it's now F, but it lost the plus, so it's F minus. Okay? Anytime you see H3O plus in your products, that is the conjugate acid every single time. Whatever's left is your conjugate base, and you will need to label those. You will need to label those. Okay? All right, now, water is amphoteric. What does that mean? Water can act as an acid or a base. It's amphoteric. It can act as it can act as an acid or a base. Well, what does that mean in the context of a Bronsted-Lowry acid or base? Well, that must mean that water can either donate a hydrogen ion or it can accept a hydrogen ion. Okay? It's special in that manner. It's amphoteric. All right, now, the Bronsted-Lowry model, checking for understanding. These are all filled out for you. I'm just going to go through a couple of them. So I wanted you to show the movement. So with arrows, show the movement, not only in the reactant side, but also in the product side. Okay, and then identify the conjugate base pairs. All right, so these are in like this molecule model. And the first one, we have HCl reacting with water. Well, HCl, we know, is an acid, so we label it, right? And what is it going to do? Well, how do acids react, or how do they behave in this Bronsted-Lowry model? They're going to donate. So with that arrow, you're going to show it pointing to the water because it's donating an H plus to the water. As a result, you draw what happens as a result in the product side. Well, the H2O gained not only an H, but a positive charge. So that's why this is H3O plus. This is H3O plus. And this is obviously in this molecular model version, how it looks in actuality, right? And if that HCl donated an H plus, what's left? Well, the Cl's left, but it lost that positive charge, so it now has a negative charge. We know the H3O plus is a conjugate acid. Anytime you see H3O plus in the product, that is your conjugate acid. Then the other is going to be your conjugate base. Okay, now, the other arrow. We have to show the movement not only in the reactant side, but in the product side. Well, how will this, if this reaction were to be reversible, how does it go back into the other direction? So a conjugate and conjugate acid and a conjugate base form, how does it move back into H2O and HCl and hydrochloric acid, HCl? Well, now let's identify what we have. Remember, this is our conjugate acid. Conjugate acids, or any sort of acid, donates. So we're going to show that movement, right? So H3O plus is now going to donate, it's going to donate an H plus. Well, if it donates an H plus, it now turns into water. Okay? And then if this Cl minus gains an H plus, it turns into, guess what? HCl. So this reaction can happen in this direction and in this direction, if possible. So that's what you're showing. Okay? All right. Moving on to the next one, NH3. NH3 is a base. Okay, it's a weak base. All right, so let's show the movement. Well, remember, Bronsted-Lowry bases, they accept hydrogen ions. So that's why we're going to show the movement. Okay, so it's going to accept from water. And if it accepts an H plus, it's not NH3 anymore, it's now NH4 plus right here. Okay. All right, now this H2O lost an H plus, so it turns into OH minus. Now, how do we know which one's the conjugate acid and the conjugate base? Well, remember, OH minus always refers to bases. Always refers to bases. Okay, so the OH minus, that's your conjugate base. Then the other one must be, the NH4 plus, must be your conjugate acid. So you need to show the movement in order for this reaction to happen in reverse. Like, yes, it can happen where NH3 reacts with H2O to produce NH4 plus and OH minus. Now what happens when NH4 plus reacts with OH minus? This will happen in reverse. Okay, so now this is the NH4 plus is the conjugate acid, so it's going to act to donate an H plus to the OH minus. When it does that, if NH4 plus donates an H plus, it now turns into NH3. And then if this OH minus gains an H plus, guess what? It turns back into water. So this reaction happens in reverse. So it happens in there's a forward reaction and a reverse reaction. Going back and forth, back and forth, back and forth. Okay? All right, and this last one, this is the self-ionization of water. Okay? Water actually ionizes in itself. So if you just have a random water bottle or a cup of water, what's happening inside that water is it's actually separating and coming back together. Separating and coming back together. So you're going to have some H plus and OH minus ions in your water. Okay, because water does this miraculous thing, it self-ionizes. Okay, and we can show that in an equation. And it's kind of weird. It's like, okay, we got water reacting with itself. Okay, well, one of the waters is going to act as an acid, where it donates. one of them are going to act as a base, or it accepts. That's why water is amphoteric, because it can accept and donate. When this happens, we get that H3O plus, right? And then the H3O plus will end up donating because it's now the conjugate acid to that OH minus, which is the conjugate base, and this reaction happens in reverse. So it breaks up into ions, then reforms. Breaks up into ions, then reforms. Breaks up into ions, then reforms. That is the forward reaction and the reverse reaction for all of these. Breaks up into ions, goes back. Okay? All right. Now, same idea here. Okay? I'm just going to do a couple of these, and then you guys can check your answers on the solution key. I'll do one acid and one base. I'll do this guy, and I'll do, this is fine, this guy. Okay? I'm labeling which one's an acid and which one's a base. Okay, so that's how you're going to start. Okay, so we're saying that H3PO4 is an acid. How will you be able to write this dissociation equation? Okay, well, let's identify the acids and bases. In this case, this is the acid, this is the base. So the acid's going to donate, show your arrows, an H plus to the water. Well, if it donates H plus to the water, it becomes H3O plus. And then plus, well, it lost an H plus, it becomes H2PO4. It's going to be minus. It's going to be minus because it lost not only an H, but it lost that positive charge. So it becomes negative. Okay, well, let's go ahead and label these. Remember, H3O plus every time, that's your conjugate acid. Then the other one must be your conjugate base. That's supposed to be base. Okay. Now, last thing I'm going to do is show the arrows not only in the reactant side and the product side. Well, if H3O plus is a conjugate acid, it's going to donate to the conjugate base, and that's how it goes back. That's how the reverse reaction goes back. Okay, and that's it. All right, let's do a base one right here. Cn minus, that's your base we're working with. Okay, so we're going to put base here, and then we're going to put acid right here, so that we know that the base accepts from the acid. Boom. Let's show that flow. As a result, that Cn minus gained an H plus, it now becomes HCN plus. Well, that H2O lost an H plus, so now it becomes OH minus. OH minus. Which one's the acid? Which one's the conjugate acid? Which one's the conjugate base? We know OH minus every single time. That's going to be your conjugate base, and the other one's going to be your conjugate acid. To show the movement, so it can happen in reverse, remember the conjugate acid donates to the conjugate base. Okay, and the reaction will happen in reverse. All right? Okay, check the answers on the other ones. Make sure you're doing them right. If you have any other questions, let me know. And then the final slide here is a new model. So we have the Bronsted-Lowry model. Now, Arrhenius came up with a different model. He's saying, okay, acids are just these compounds that contain hydrogen ions. That's it. We're not saying they donate anything. We're just saying that in solution, there is hydrogen ions if it's an acid. And then he's saying that bases are compounds that contain hydroxides or form that hydroxide ion in solution. Okay, so here are your examples. So HCl, when it dissociates, you will see H+. If you see H+ in solution, or I should say you detect H+ in solution, then it's going to be an acid. If you detect OH- in solution, it's going to be a base. Okay, this is Arrhenius's model. It's a little bit different, okay, because this is the only fact he's basing it off of. Okay, and we're going to work with Arrhenius models in the next PowerPoint presentation when we talk about strong acids and bases, and that's going to be our last kind of concept for the year is strong acids and bases. Okay, but we don't have to worry about those for the quiz on Wednesday. All right, so tomorrow I'm thinking about giving you guys a little bit of practice so you can practice for the quiz. And then if you have any other questions, don't hesitate to email me. All right, see you guys.